Team Cyborg from Group 5, and we are conformed by Alessandra de Zubeldia, Cecilia Padilla, Ángela García, Amanda López, Kevin Montero. We will be presenting the exercise 1 of compound interest for the partial 1 project of trigonometry.
Montero, we're the cyborg team. Okay, we're going to present the flowchart for the compound interest exercise 1. First, we have to identify the rate and the periods. 3 years, quarterly, 3 times per year, and the rate is equals to 8.5%. After, we have to identify the formula. A equals P times 1 plus the rate, that is 8.5%, divided by the periods in a year, at the power period times time. Replace the data given by the formula. A equals P times 1 plus the rate divided by the year at the power of the year and plus times time.
Now here is our problem. A man invests $5,000 in an account that pays 8.5% per year. First, the letter A. Find the amount after 3 years if the interest is compounded quarterly. So, here we have the formula for compound interest, where A is the amount of money accumulated in N years, P is the principal amount, the money that you invest at the start, which is $5,000, 1, which is part of the formula, R, which is the annual rate of interest, N, which is the number of times the interest is compounded quarterly, and finally, NT, T is the number of years that it is actually in the account, which in this case is 3 years. So now we have to substitute all of our information within this formula. P is $5,000, which is what the man first put into his bank account. Then we put 8.5%, which is the interest that he receives for having his money in that bank. 4 because it is compounded quarterly, that means 4 times per year, that means every 3 months. And finally, here we have the compounded quarterly, which is 4, and 3, which is time, 3 years, because he has it inside of that bank for 3 years. So once you substitute these and you do the operation, here you get 5,000, 1.02125 at the 12th power, you get the amount after 3 years, if the interest is compounded quarterly, is equal to 6,435.09. So this is the money that the man will have in his bank after 3 years.
Now, how long will it take for the investment to double when compound quarterly? So, based on this formula, we're only going to change the value of P and double it. That's why we had 10,000. And the equation stands the same. Now, because we need to clear out T, we're going to divide 100 between 10,000. And we had this. And multiply 4t over 1/4, and this we're going to make in the other side. And we had t is equal to 1/4 logarithm 1.2125(2). And now we need to do the change of base between log 2 and log 1.02125. And we had this result.
And now we have, if the interest is compounded continuously, how does the answer to B change? This is the formula to the compounded continuously. It's A, it's the amount of money accumulated after N years, and P is the principal amount, E, Euler's number, R is the rate, and T is the number of years. So we have, first we have 10,000. That is the amount when it doubles. And here we have the first amount, that is 5,000. So to clear E, we we divide 10,000 by 5,000 and we have 2. So we eliminate this from here. And now to eliminate e, we use a natural logarithm and we eliminate e. And now we have natural logarithm of 2 is equal to natural logarithm of this. So now all we have to do is clear t. We divide this over this, and we have time is equal to natural logarithm of 2 over 0.085. And this is the answer.
We needed to graph, so we changed the logarithmic function into an exponential function. In order to do so, we use this formula, where RO means initial factor, E means Euler's number, R means rate of change, and T means time. So the multiplication between initial factor and Euler's number elevated at the power of rate of change multiplied by time will give this formula. And now GeoGebra does not accept that formula, but we searched for another online graphing website and we got a graph.
This project helped us analyze and solve a real-life problem related to money and economics, compound and continuous interest rates of money. Now we are able to comprehend and obtain these two different types of interest rates and apply them to everyday situations, which we will most likely encounter in the near future when we run our own households, receive our paychecks, and buy and invest in different products, services as adults. The use of logarithms helped us solve this problem and therefore make logarithms highly useful for obtaining the answer for problems in our daily lives.